Hey, good morning, fellow nerds, and welcome to another episode of Between Two Nerds with me, Jeff Doyle, and with my good friend Jeff Tansura. Good morning, Jeff.
Good morning, Jeff. How are you doing? How have you
I'm
been?
doing great. Just enjoying the schizophrenic Colorado spring here, where it's 80 degrees one day and snowing the next, and then 80 degrees the day after that. And I think you get a little more consistency there in California, don't you?
Yeah, it's pretty nice. It's actually summer. We are in high 80s for. We've been
Oh, yeah.
really summer mood for last week or so.
Yeah. We've got another few weeks before we're officially summer, I guess. So, for all of you listening, I would ask this question: how often do you get to learn a new routing protocol? You certainly, probably, if you're listening to this show, are very well versed in BGP and OSPF and maybe ISIS and EIGRP and all of those kind of things, and you've known those things for maybe years. And you certainly know that this is significant, by the way. You certainly know the ins and outs of distance vector protocols versus link state protocols. And you know simple things like the fact that even though BGP is called a path vector protocol, it's really just distance vector. We're going to look over this session and the next few sessions at a new routing protocol specifically for the data center called Routing in Fat Trees, or RIFT. And we're really privileged to have, as it turns out, the chairman of the IETF RIFT working group. And where is he? Oh, that's you, Jeff. So, you'll be hearing a lot of this right from the horse's mouth. And so we're just going to take off on this, and maybe a place to start. We've been over, I don't know how many shows now, been talking about BGP EVPN and BGP specifically. Well, not specifically, but a part of that, an aspect of that, is BGP in the underlay, which is, we've made the argument that BGP is certainly the best alternative, specifically eBGP, for running the underlay in the data center right now. But there's also, there are some, I don't want to call them liabilities, but some shortcomings to BGP in the underlay, which also brings up the question of, and we'll talk about that. What are those liabilities, and do IGPs, specifically link state IGPs, offer better alternatives? The first thing you might have noticed when we've talked all along about BGP in a CLO environment or a fat tree environment, whichever term you like, is things like, where every single switch is its own autonomous system. The spine layer is its own autonomous system. And you know what an autonomous system is, and that just sort of carries the smell of something BGP created for one purpose, which is routing in the internet, and kind of shoehorned into a different purpose. The implication being there, BGP is not really purpose built for what it's doing in CLO environments in the data center. Would you agree with that, Jeff?
Yeah, so BGP has been around for a long time, and as with IGPs, the assumption has always been sparse connectivity. Right? If you look at internet, you don't have everybody connected to everybody else. Usually you've got a number of ASBRs that provide connectivity between autonomous systems, but practically it's nothing like connectivity in data centers. And this really, really dense connectivity brings significant, I wouldn't call them issues, but challenges with regards to both BGP and existing link state IGPs.
Yeah, and probably right there at the top, if you look at distance vector protocols, BGP in this case, versus link state protocols, OSPF or ISIS. For BGP, you have something that is highly scalable, but at the same time, and there's exceptions to this, but it tends to be slow, and it tends to be subject to things like path hunting. In data center environments. Link state protocols, on the other hand, tend to be very fast, but are not very scalable, which is why as they grow big, everybody knows this, you have to start configuring areas and things like that to get that scalability under control. And the main problem with that scalability is information flooding. Changes, that even minute changes that happen within a single area in link state mean flooding throughout the area. Partial SPFs, by the way, alleviate a little bit of that. But nevertheless, you get all of this flooding and everybody having to recalculate the SPF for something that might have been just a simple topological change. That's not a good thing in the data center. Jeff, I'm sure you can think of a lot of other liabilities on both sides, right?
Yeah, I think there's also another development, right? If you are looking at small to medium data center, probably you could run away with static routes, right? It's not a problem. If you look at a bit larger data centers, and there's another point to that, we finally started to connect endpoints or servers over layer 3, actually doing routing. We see more and more deployments where there's connectivity from server into fabric that exchange routing information. If you think Kubernetes, this is predominantly model. So if you look at Calicut Agera, they'll provide BGP between fabric and the Kubernetes cluster. So we see more and more routing. So suddenly, rather than seeing your endpoints being just leaf spines, super spines, you see, 40, 80 servers per rack, all speaking routing protocols. So number of routing information to be exchanged is significantly higher. And this is what brings a lot of pressure on existing routing infrastructure, especially at scale.
Yeah, that's a really good point, that if you start pushing your routing protocol down to the server level, you are hugely increasing your scalability problems. At the same time, there's an advantage there. We've talked in previous sessions about multi-homing, multi-chassis, multi-homing, and potential solutions there, which tends to be a very fragile problem. When you're trying to multi-home servers to multiple leaf switches, and if you can run a routing protocol down to the host level, the server level, you can eliminate a lot of that. But you pay a very distinct price if you're doing that with BGP.
And back to IGPs, the only way to abstract or hide information is to create boundaries.
Yeah.
And building multi-level, multi-area networks in data center makes little sense from complexity perspective. So rather than building this somewhat artificial boundaries, because cloud topology as such doesn't really have this boundary, the idea was to build protocols that would provide the state reduction naturally within protocol.
Yeah. And something that is that strikes me is, if you look at the basic problems, the basic liabilities, I don't like that word, but I keep using it, of link state versus distance vector in CLO topologies. The real problems with distance vector purely distance vector, are manifest themselves primarily at the upper levels, at the spine or supraspine. Whereas it seems like the problems or liabilities of link state protocols manifest themselves primarily at the leaf layer. And this is kind of roughly getting us into what Rift does. Is Rift actually takes advantage of, so I want to say it takes advantage, yeah.
Directionality. It's direction aware.
Exactly, yeah. That it at the upper layers, Rift is mainly or very similar to link state. And at the lower levels, Rift is primarily distance vector. So you've got this hybrid protocol. Is hybrid the right word for it? Hybrid, at least in terms of distance vector versus link state.
It is exactly the right word. Yes.
Yeah, and so it's taking the best of both kinds of routing protocols in the data center, and maybe that's a good launching point for Jeff. You've got quite a few slides here, and maybe this is a good launching point to start talking about exactly what Rift does. And kind of helping everybody get their heads around the idea that, okay, it's link state at the top and distance vector at the bottom.
Yeah. So before we continue, the agenda is to start today with what's going on data center routing in general and touch upon Rift. Next meeting, we are going to invite our own Tony P, or Tony Pshenda, if you can pronounce his family name, who's pretty much invented the protocol and coded most of it. And he is going to go into great details about how protocol formats look like, why have we used Rift in coding there, and potentially into disaggregation scenario. So there's a lot of to be discussed. The intention of today's podcast is to explain you what's going on and really start this really interesting series of podcasts about routing in data center, which we will be doing over the next 3, 4, 5 months probably.
Yeah.
So some history here. We started building data center a long time ago, since compute existed. Most data centers till 2000 were layer 2 with spanning tree. Eventually, we started to introduce layer 3 at top layer. Most deployed protocols were EIGRP on Cisco side and SPF in general. Public clouds, or actually Google, before started building out their infrastructure significantly in the beginning of 2007, 8. This is also when first white paper about cloud topologies had been published by, few more people at Google. They started to move to layer 3. As they were looking into open source implementation, the only protocol available at the time was BGP. And pretty much the only code base is Quagga, right? So on one side, BGP would naturally fit because of its richness in policies and ability to scale. On another side, practically, it was the only open source protocol available. There were no ISS or SPF implementation that were open source, or even if they were undeployable pretty much. So if you look at what happened starting from 2010 to now, Amazon implemented routing. It's not publicly known, but they do run SPF. Facebook is running partially BGP in a lot of space, moving to OpenR, which is a protocol invented by Facebook. And it is link state, but has some very interesting properties. And by the way, if there's interest to talk about OpenR, potentially we could ask Piotr Lopachov to join us and talk about OpenR.
Yeah, I'd love to hear about that. And I actually didn't know that about Amazon, by the way.
I'm not sure it's publicly available information, but anyway. So what happened in ATF in 2012? Saint Piotr Lopachov published BGP routing in large DC. It described really implementation of BGP in Microsoft Flutter, worked at the time and wasn't really progressing. So after 4 years in routing working group, we decided to adopt the draft and we published RFC 7938 that became pretty much the handbook or Bible for a lot of people who deploy BGP in data centers today. So I'm really proud of this work done. Around 2015, 2016, in routing working group, we started looking into what really needs to be done in data centers that keep on growing. And we've come together, so a number of people who are building protocols, number of people who are deploying protocols, really to put number of requirements against which we could build protocols. So in 16, we had first initial ideas about what we want to do in data centers. So there's Rift and BGP SPF, so-called LSVR. We'll talk about it as well at some point. And they also proposed first modifications to existing IGPs, mostly with regards to flood reduction. So the main problem of IGPs, as Jeff said, is really flooding. And as you go up into, and especially if you start looking into larger fabrics, 5-stage, potentially 7-stage, the amount of flooding becomes unbearable.
Yeah.
Right. So in 2017, we had a BOF at ATF 100, great number. And as a result, we formed 2 new working groups. One of them is Rift, and this is one we are going to be covering today, probably next to podcast, and LSVR. That is really BGP, where best path selection is replaced by Dijkstra. Jeff, sorry, I cut you.
No, I sort of started a little early there. I just wanted to mention that, and I'm sure everybody in the audience is aware of this, which is beyond the history that Jeff is showing here of routing in the data center. There's a whole arc of how the data center is used over this time period. Early on, early data centers, 90s, early 2000s were hierarchical and could be hierarchical, and you would see a lot of best practice designs around that because it was primarily serving traffic in and out of the data center. With the advent of virtual machine mobility and things like that, and the advent of spreading different parts of any one page's content across different application servers and that sort of thing, a lot of the traffic, and maybe probably the majority of traffic in a lot of data centers, was east-west. In other words, between different servers within the data centers. And that imposed an entirely different set of requirements, not only on what the data center topologies look like, which is where CLO came from, but a different set of requirements and needs of the routing protocols within the data center virtual overlays.
So what you see here is, it's 3 years old data, but I assume it's still somewhat representative. So we've done large research around what enterprises run, and this is the result of 2017. So 70% run SPF, 45%. So you see more than 100% here because of difference in people who responded. But practically, OSPF is prevalent protocol, EAGRP was number 2, and then BGP and others, about 50%. Right, so there's a lot of work to be done, and probably you don't want to run OSPF or GRP in large data centers. And we discussed in many different ways why not. So we put together a draft that survived only one version, but really was meant to bootstrap, work, and clarify what needs to be done. So we called ourselves the Synaptic protocol design after another protocol that was designed on the napkin. And not only because we are long-time friends, we actually know how to build data centers. We know how to design protocols. So if you look at people who made the team, most of people are prevalent protocol coders and great network architects.
Isn't that Russ White over on the left there?
It looks like. So again, we've been having this discussion. My LSAs are better than your LSPs, and around the internet. The intention was to have common set of requirements that every existing new protocol could be compared against. So we really didn't want the beauty context. And you talk to any network engineer, you get very, very opinionated opinion about what it should be. So the idea here was to provide set of requirements that are protocol independent, and we could compare them independently.
I had a conversation a couple of days ago on an entirely different topic. It was still IT, but really didn't have so much to do with protocols at all. But the topic was around the fact that everybody seems to have their favorite solutions, their favorite protocols, and that sort of thing, and nobody really addresses. Or nobody seems to start with what problem are you trying to solve, rather than just saying, I really like OSPF or I like ISIS or, but starting with, and this illustration just made me think of that, of really starting with, well, what's the problem you're trying to solve?
Exactly. And looking 10 years ago, pretty much anything would do outside of 2-3 large data centers, right? Looking at scale today, what is expected with Kubernetes deployment, what's expected in Telco Cloud, we really need to look much, much closer into what problems we are solving and whether existing protocols or solutions can address them. And for many people, it means getting out of their comfort zone, learning new things, and this is what we are trying to facilitate here, really to tell you what's going on and why it would be a better solution potentially than something that we all familiar and love. So this is a pretty old picture, but we are far from, probably we are now in, early teens. Mm-hmm. We've got number of implementations of different new protocols, but we are still looking forward to new work, to requirements, to questions. So please hit myself, Jeff. We would love to talk about all those problems in more details.
And it might be worth mentioning, I don't know, maybe this is the wrong place to mention it, but you can get your hands on Rift implementations. There's a evaluation version available through Juniper. There is a public version, I think, that runs on Linux and Mac OS, if I remember, that's available. And it's a great time to actually, if you're a router jockey, it's a great time to download it, play with it, kick the tires, and see what's right and what's wrong. And as Jeff said, start contributing to that.
So as we're progressing, we will share all these resources to you, as well as we've published day one book on Rift, 400 pages of, it's really well written book, a lot of good information. It's very readable, so we'll share this information as well. It's downloadable, there's no paywall, so please read it. And again, great book. So this is a short presentation of what we have today in networking, and Jeff described it really, really well, so we're going to spend a lot of time here. So really, we've got distant vector protocols. So it's tell your neighbor, rest of the network. There's link state protocols, tell rest of the network, your neighbors, and then BGP, which is path vector, that path described by sequence spaces in ASPath. So if we look at link state protocol, they do distributed computation, meaning everybody has full view within their particular level or area and perform computation on top of this topology. We've got topology elements such as nodes, links, and prefixes distributed across all the nodes. Each node will originate LSA or LSPs with its own element. Newest version always wins. And again, everybody sees whole topology. That's why when we do traffic engineering, we use link state protocols, because we need to ensure consistency of databases used to compute end-to-end paths that is loop-free. However, disadvantages here are that every significant change shakes whole network, since LSDB or link state database has to be identical on all routers across area or level. Everybody needs to be notified about particular change.
I just wanted to emphasize one of the huge advantages here is that each node, as Jeff said, and as is on the bullet points here, each node sees the whole topology. And ages ago, when I was teaching network basics classes, that was one of the things that I emphasized as a difference between distance vector and link state, is that link state is like looking at a map of the entire network, whereas distance vector is simply, as the word vector implies, is simply some directions to get to a point. Go this direction and this many hops, and eventually you'll get to your destination. And the reason that's important is because if you have a full picture of the entire topology, it's much easier to avoid loops.
So the main disadvantage in leaf-spine topology is really flooding. It's excessive, and the larger the fabric, the more flooding there is. So if we look at both protocols, ISS has so-called mesh group, which is a hack on top of ISS to reduce amount of flooding in NBMA topologies. OSPF has none, so practically you always flood. And going forward, we'll hear about improvements brought to IGPs by flood reductions. Diffuse computation, DFB. The examples are BGP, RIP, and IGP. Prefixes, as they traverse throughout the network, gather the metric, and they pass it. This is how loop prevention is also implemented. Every node in the graph in the network will look into IS path. So we're talking BGP here, and look for its own IS. If it's on IS present, it's a loop. It drops the update. If it's not, it's going to be computed and flooded. It's very well suited for policy, and we know BGP, besides doing reachability, it's mostly policy protocol, right? It happened to distribute reachability, but in large internet, it's mostly used for policies. Due to its properties, it scales much better than link state protocols. It can scale to really, really large numbers and implement top of TCP to provide underlying layer of streaming, of ability to build many updates. In both IGPs, you've got hard limits with regards to size. In the ISS, it's LSP count. In the OSPF, it's LSA type 1 size. And BGP doesn't have inherent limitation. There are implementation today that support 500 million routes. Right? So the problem here is relatively slow conversion. So let's review why. If we take a link state protocol, it does two things in parallel. When it receives an updated copy of LSR LSP, it will immediately flood it to its neighbors. It will also go and process it locally. So both functions are happening in parallel. And eventually, after conversion has happened, every device will agree on same topology because everybody has same topology and runs same algorithm of this topology, right? So the updates are very fast, and eventual convergence happens when every device in the path between source and destination has processed these updates and built new graph, new topology. If you look at BGP, the rule is you receive an update, you process it first, and then you advertise it to your neighbors. So there is no flooding for prefixes that have been not processed. The idea is that you should only advertise prefixes that you are using for forwarding, because otherwise you can create a loop. So this would be pretty naive implementation, obviously, because then it will take forever. So there's a lot of optimization in implementations, but practical rules are still the same. Receive, process, update, advertise. And obviously it takes more time as long path getting longer, right? So the longer is the path of advertisement, the longer it takes for a prefix or an update to be advertised. So at scale, it could create potential issue with regards to speed of update propagation.
And all of you have probably heard the it's really kind of ancient at this point, but the description of distance vector protocols as routing by rumor, because all you really, and you can see that easily in the graphs here, all you really know, all that a node knows is what its upstream nodes have told it.
So what we are going to be talking for the next, actually, we started with leaf-spine topologies, and we'll keep on talking about leaf-spine topologies. In 1950s, work done by Charles Clough, and obviously today is prevalent topology that could go from very small 3-node networks to networks with hundreds of thousands of switches, building more layers with wider radix. How are we doing on time?
We've got maybe 10 minutes, a little more than 10 minutes left.
So let's start with Rift. It's a routing protocol for leaf-spine networks. Why leaf-spine? Because it leverages awareness of the direction. In data center, we've got direction that is east-west, meaning it's horizontal. And we've got north-south, that's vertical. Practically, east-west connectivity is within the fabric. South-north is from fabric to outside. So Rift is built on assumption that there's direction. And we will see how it's leveraged in terms of behaviors, how we, based on the direction, change phase of the protocol being distance vector down, so reducing amount of information to default route only, and link state up, where top of the fabric or super spines know exactly everything about the topology.
The second bullet there, I just wanted to say automatic disaggregation. If for those of you in the audience, if that if you're not sure what that means yet, we'll go quite a bit more into that, and that's a really key concept here.
Yeah, and it took a lot of time and effort to figure out how to do it properly, and probably topic of summarization data center deserves its own episode to discuss. I think we talked about bad sides of aggregation in leaf-spine fabrics in one of the BGP shows. So Rift is the first protocol that would actually allow you to aggregate and would disaggregate on demand, meaning when there is a failure, protocol itself will go and provide longer routes, not to black hole. So we are going to discuss it in great details. It's one of the most innovative topics in Rift. Yeah, that's one of my favorite. Right. So when we started with Rift, we had many discussions with different people about whether we should enhance BGP, we should enhance SAS, and really, it was very difficult to reach agreement across people who, to some degree, invented protocols, worked with them for 30 years, and at some point we just decided to build it from scratch. Well, the best way to predict the future is to build it, and this is exactly the idea behind Rift. Rather than trying to reuse or enhance existing protocols, we decided from while leveraging existing protocols. So if you look at behaviors in Rift at a left side of it, it reminds of OSPF a lot. If you look at how it goes down, it's nothing else than glorified Rift, right? So we invented new paradigm, but leveraged 30, 40 years of science and understanding of how existing protocols work. Now we are going into comparison here. So as we talked before, we've created draft DC routing requirements to have this list of requirements to be able to compare against. So zero configuration was very, very important one, and Rift provide full ZTP. You just need to identify particular layer in your network. So for example, you say these two switches are super spines, and then by propagation of data comparing their level to one received, full fabric could derive where they are. Moreover, it will also figure out if you try to connect switches horizontally, which is not allowed in this spine network, right? So you get full zero-touch provisioning, and there's some new work we are going to cover later. Rift also allows you to fully configure EVPN in the fabric. So peer discovery, forming of trees, all built into the protocol. As we said, we reduce amount of state going down. We keep same amount of state going up. Why is this important? As you hit the server, you don't want to have 20,000 routes on the server. Doesn't make sense because server could go left or right, one leaf or another. What you do want to have, you want to have two default routes. Moreover, if something fails on one side, you would like to be notified about this failure. How we do it in list by network, you get more specific routes on the active link that didn't have any failures. And that's exactly what Rift does. High degree of the CMP. Very important point, Rift is loop-free per definition. So you don't need to use the CMP. You actually can send traffic over every link. Rift guarantees loop freeness. Rift gives you also cumulative metric. So remember, when you use BGP, you load share per flow. You don't take into consideration bandwidth available. There is a way to do so throughout what we call DMZ community. It's really a community that's attached to a route that describes bandwidth available upstream and allows you to provide weighted CMP. So now we are going to hash based on the weight of the route, not only reachability. It has a number of issues. The initial community has been defined as non-transitive, so it wouldn't work in eBGP. Number two, in BGP topology as such, as you traverse, your network is not cumulative. So if you're 2, 3, 4 hops away, practically you don't know. The network becomes meaningless. So what you need to do is to provide accumulation of metric at every hop you traverse. Right? There's some work done. It's more implementation than standard. There's also draft published by, I think, Arista folks. So they do it, but practically you need to hack around. So you need to take initial metric, add new one, and as you go down, you'll get cumulative number that could be used for load sharing. Rift does it dynamically, and it's built into the protocol. What else? It has ability to propagate key value information in what we could call It's similar to APEC LSAs in SPF, right? So it gives you ability to propagate all kind of information that's not directly relevant to routing, but it's very useful. For example, for segment routing, we are using exactly this information to distribute binding between prefix to label. Right? So it has built-in in-band way to distribute all this information. As we said, there's automatic disaggregation and failures, what we call positive disaggregation, as well as negative disaggregation, which is topic for entirely another discussion, and minimum blast radius on failures. Because when there's a failure, you only notify layer on top of you. No one else needs to know. If you compare it to IGP, link state IGP, everyone will be notified. So only one layer on top of you aware of the failure happening. There's no propagation end to end. And very, very fast convergence. So in our internal test, we could see convergence, and it's a protocol convergence, not something like fast rehash within 50 milliseconds, just based on how fast failure information could be distributed.
That might be a good place. We're a couple of minutes before the top of the hour. That might be a good place to stop, and we can dive into the general terminology in our next session.
Great idea. Yeah, I agree with you.
In the few minutes we do have left, does anyone have any questions? Haven't seen anything pop up, so this is probably a good place to wrap up. And I love that chart, by the way, that you just did, and there are like 15 questions that popped into my head that are probably best saved for the next session. But Jeff, thank you so much. And as I said before to the audience, Jeff is the chairman of the Rift, chairman or co-chairman?
Co-chair.
Co-chair of
my chair is Jeffrey Zhang.
Okay. And of the IETF Rift working group. So you're getting firsthand authoritative information here, and I hope this is useful to you, and I hope that the sessions moving forward are useful to you. And in the next session, we'll get into a lot of the details. We've talked about the advantages of Rift and what it does, and we'll in the next session get into the details of just how exactly that works. And
thanks everyone. Thanks Jeff, and we'll see you in 2 weeks. And yeah, I would expect Tony P to show up and provide us much more information with regards to low-level details implementation, and it's really exciting.
Fantastic. See you in 2 weeks.
See you in 2 weeks. Thanks, everyone.